Good morning, dear learners, and thank you, everybody. In the last two videos, we discussed Cartesian coordinate system on 0 dimension, 1 dimension, 2 dimension, 3 dimension. And we also discussed a polar coordinate system in 2 dimension. Today, we will try to extend polar coordinate system from 2 dimension to 3 dimension. And by this method, today we are going to discuss cylindrical coordinate system in polar coordinate. Cylindrical coordinate system. Cylindrical coordinate system. Actually, this is the extension of polar coordinate system from 2 dimension to 3 dimension. So, before discussing this coordinate system, at first we again try to bring Cartesian coordinate system in 3 dimension. So we know that the Cartesian coordinate system was in 3 dimensions like such. If we denote this axis by x-axis, this by y-axis, and this by z-axis, and this is the origin for Cartesian coordinate system. If we take a point on this xy plane, such this point is p, x, and y, then we know that the measurement of these points with respect to this axis are, if we draw a perpendicular to x-axis, that is, this angle is 90 degree, and we denote this amount by the abscissa x, and this amount by the coordinate y. And finally, from this point on xy plane, we move along z direction upward or downward. If we move from this point to upward along z axis, then there is a point P whose coordinate will be x, y, and since it makes along z axis, then it will be by z. Therefore, the point will be P, x, y, z in Cartesian coordinate system. If we remark this length sequence by reading, this is x, this is our y, and this is our z component. This is z component. So this was our Cartesian coordinate system. At first, we move from origin to the point on x-axis against this projected point, and from this point we reach here at projected point of this point, and from there we can move upward or downward direction or making z. Then we have finally defined p, x, y, and z which is the coordinate system of Cartesian in 3 dimensions. Now, for discussing cylindrical coordinate system, at first will form a cylinder. Suppose we have a cylinder like such, right circular cylinder. Here, this is the right circular cylinder. We make a right circular cylinder. Now, we consider that this point is the center of the base of the cylinder. And from this point, we draw two axes. One is y-axis, and then one is x-axis. So, this plane is xy. Now, if we would like to locate a point on this cylinder by only two-dimensional polar coordinate system, then we see what will be happen there. And that is, can we able to measure this point on the curved surface of cylinder by only two-dimensional polar coordinate system? We check it. Suppose a point on curved surface of cylinder P, whose projection is doing like such on xy plane. So the projected point is here. Say this point is P prime. Here also P prime. Now, in two-dimensional polar coordinate system, we know that this is pole O, and the distance from this pole to this projected point will be denoted by R. And this R makes an angle with the positive axis will be theta. Then this point will be denoted by R. Therefore, we can say that the coordinate of this point will be R theta. Coordinate of P will be R and theta. But if we analyze this in another way, so that suppose here is another point Q on the curved surface of cylinder. Now, if we draw a projected line on the xy plane, then we get the similar point P10, and which makes polar distance R and polar angle theta is similar to previous point. So we can say that the coordinate of Q will be R and theta. But we know that in every space, single or two-dimension or three-dimension, for every two different point should have a different identity or different location. But here we see that P and Q are situated at different position in space, but their coordinate will be same, which is not possible. If P and Q are different point, then they should have the different identity. That is why from here we can conclude that actually we cannot measure this point on space or curved surface on cylinder only by two-dimensional polar coordinate system. Here we need another parameter or another axis to find out or locate these two different points properly. And this parameter is actually, if we go from this point on the plane xy point r theta, if we move from r theta to the respective point we have made a height which is denoted by z. That is, the coordinate of P will be P, r theta, and z. That is why we will have to draw another parameter or axis through the origin, which is vertical line, and this is called z-axis. So if we move from this point to the respective point, then we have made an height r which is denoted by z, and this height will be different for the point Q. Actually, here the height of this point Q is less than z. Here this point is z. So if we proceed in this way, then we can be able to express or denote or locate or identify two different points by two different coordinates. One is r theta z and one is r theta z1. These two are different identity of these 2 points. Now we go back to this figure. This figure was described under Cartesian coordinate system. Now we would like to discuss this in polar coordinate system. In 2 dimension, we can say that this point P is situated from the pole with distance r, and it makes an angle with the positive axis theta. Therefore, on x-ray plane, the coordinate of this point will be P dash r theta in 2-dimensional polar coordinate system. And we show here by 2-dimensional polar coordinate system, we cannot measure a 3-dimensional point P, which is situated on curved surface of cylinder. So, if we have to measure this point correctly or properly, or locate it in proper way, so we have to make another axis along z axis, which is already shown, which is here. Then the point P will be in polar coordinate system is P, polar distance r, polar angle theta, and the vertical displacement or height will be z. So here, if we describe in polar coordinate system in 3 dimension for cylindrical coordinate system, the r will be r is the distance from pole O to the projected point is dash from or of the respective point P, and theta is the angle of pole or positive x-axis with the polar distance r, and z will be the height of P upward or downward direction. This point can be situated at the right position of this x-y plane, and it will be negative. So that is the height of the upward or downward direction. This is the description of cylindrical coordinate system for a point P, R, theta, and Z. I would like to again just say that if we want to reach this Cartesian position of P, then first we have to make a point on the xy plane on x-axis and y-axis, which is P dash xy. Then from this point we have to move along this z direction. We have to reach the point by the height z, and we can reach at P xy z. The Cartesian coordinate system. And for polar coordinate system, in 3-dimensional, first of all, we have to make this point on xy plane by joining pole and the connected point P dash, which is called R, and then make an angle with the positive axis theta. Then we can make this point P dash R theta. And from this point, we have to move along that direction. Then we can reach at this point P, which is R, theta, and Z. And this point is the cylindrical point or a point in cylindrical coordinate system. And for each every 2 points, they have different identity or notation. You can see there point or every point of this line will be different position or different identity or different location by the height z. If the points are located in downward direction from the xy plane, then this height will be negative. Physically, if we want to reach this cylindrical point P from this coordinate system, so we have to make a mechanism from origin. Since it is R, which is polar distance or the del vector, we can also say that this cylindrical curved surface also intersect with x-axis cap and intersect with y-axis cap. So we can say that this amount also will be R. This amount will also be R. Now, if we start from origin O, we reach from O to this point, then we can make R. The first thing of this point R. And if we move along this R, so we will be able to make an angle theta, which is the second angle theta. So we have to reach from here to where P and dash, which is R theta. Now from here we can easily reach along z axis, which is the height of this point here. Finally, we can reach at P R theta z. Again, I said that first of all, we have to move from origin to this point, then we can make R. And from this point on x-axis, we move theta direction, and we can reach at this point, we just R. And from the point on this plane, xy plane R theta, we have to move along that direction, then we can reach R, and this, and we can find out this position from the origin. It will be a mechanism. It will be a mechanism for finding a point in three-dimensional cylindrical coordinates. Here, one thing is very important. We know that in polar coordinate system, R is always non-negative. But in polar coordinate system, certainly three-dimensional for cylindrical coordinate system, here R can be negative. Suppose this is radius of this cylinder R. Now, if we move in the backward direction, this is by minus. So if this is divided by minus r and this is divided by plus r, then we can say that diameter of this cylinder will lie between minus up to r. Minus up to r. The diameter of this cylinder lies between minus up to r. So if we want to reach this location from minus r position, then what will be the mechanism to reach that? We see that if we move from minus here, then first we move from pole to this point on x. Then we can make an angle with the positive axis for this radius vector of this r. We can say that we can reach here by this angle theta plus twice pi. Theta plus twice pi. By making an angle theta plus twice pi, then we can reach there. And in previous system, we saw that from here we can reach this point with the height there. So from minus r, we can also reach the point in this way. At first, we move from a pole to this point, which is position minus r. Then we make an angle anti-clockwise with this polar distance r, which is theta plus twice pi. Now we have here at this point on x-y then r theta, and from this point to the respective point we can reach in the right z. So we can say that in cylindrical coordinate system, a point have two identity, or even by two methods we can reach that. So another representation of P will be P minus r theta plus, here it is pi, theta plus pi, and z is constant. This line makes an angle with this opposite is, here is theta plus 1. It is theta plus pi, and that is also. So we can conclude that in cylindrical coordinate system, a point have two identity, or in two ways we can measure it, and we know that in polar coordinate system, identity of a point will be infinite, which was P r theta plus twice and pi. So for the following these characteristics, we can say that in cylindrical coordinate system, a point will be a two-faced type of identity. Here also we can identify this point by this method. Q equals Q minus r theta plus pi. Also that one. This is the distinction of describing a point in cylindrical coordinates. Now we would like to switch point from polar to Cartesian, also Cartesian to polar. First, we would like to switch the point from polar to Cartesian. In cylindrical coordinate system, polar to Cartesian. We have to observe this figure carefully. We have r, theta, and z, and we have to find out the value of x, y, and z. Here one thing is very clear. In both coordinate system, Cartesian and cylindrical coordinate system, they are equal to. Now, if we consider this triangle, since it is perpendicular from PJ to x-axis, so this angle is 90 degrees. So from this triangle, we can say that cosine theta cosine of theta equal base divided hypotenuse. Base is x, hypotenuse r. So x equal to r cos theta. Again, if we apply theta sine ratio, will be perpendicular divided hypotenuse. Perpendicular y hypotenuse. So y is r and theta. So we can easily calculate from polar to Cartesian in this relation. X equal, therefore x equal r cos theta, y equal r sin theta, and z equal, this is the relation between polar to Cartesian coordinates. X equal r cos theta, y equal r sin theta, and z equal to z. Again, for Cartesian to polar, Cartesian to polar, we also observe this figure. We have x, y, z, and we have to find out r, theta, and z. Here is also z equal to z. These are staying in both coordinates. And from this triangle, we see that since it is right angle, then it is hypotenuse. So we know from Pythagoras, r square equal to x square plus y square. X square plus y square. So r equal to plus minus square root x square plus y square. Here we have taken plus minus sign, and because in cylindrical coordinate system we know that every point has two identity, or in 2A we can just write a point or not a point. That is why we have here two value of r, one is positive and one is negative. Also, if we use this triangle, we have tan theta equal y over x. Y over x. That is theta equal tan inverse y by x. Therefore, we can use this relation for finding polar coordinate system from Cartesian coordinate system. That is, we can say that r equal plus minus square root x square plus y square, theta equal tan inverse y by x, and also z equal to z, which is constant or similar in both coordinates. So these are the relation between for switching from one coordinate system to other coordinate. Now, two questions will be arranged in simple way that why this is called cylindrical coordinate system. Follow dear learners. Every point on the surface of the cylinder, we see that one thing is fixed, which is r. Everywhere, this is r. At any point on the curved surface of the cylinder, will be divided by the polar distance, which is r. Theta and z can be changed, but r is everywhere fixed, and which denotes the radius of the cylinder. Since r is fixed everywhere of this curved surface of the cylinder, so we can say that these are represent the radius of this respective cylinder. That is why this coordinate system is called cylindrical coordinate system. And another question is, where can we apply this cylindrical coordinate system? We can apply this system anywhere. As for example, in physics, we have to measure magnetic field, electric field, temperature field, and another thing like divergence, curl, gradient. For every case, we can use this coordinate system, and we get the fruitful result by observing or by practicing this coordinate system. Now let us take an example for switching Cartesian coordinate to polar coordinate. Suppose we have a point which is Cartesian point 1, 1, 1, and 5. We have to represent this point in cylindrical coordinate point. So we can use this relation. This relation was that 1 is x, also y is 1, and there is 5 in Cartesian coordinate. For cylindrical coordinate system, we know that r equal to, we know that r equal plus minus square root x square plus y square. 20 plus minus 1, 1 is square root. And theta will be tan inverse y over x, which is tan inverse 1, and this is pi by 4. And we know that there is then that 5. Therefore, for one point r theta z, the point will be so 1, 1, 1 equals to in polar coordinate system, that is r square root 2 theta pi by 4, and finally z is 5. And in another format, 1, 1, 5 will be simplified minus r, then theta plus 5, theta plus 5, theta, that is 5 plus 5, and that is then 5. So we have minus root 2, 5 by 4, and 5. So for Cartesian point 1, 1, 5, we can shift this point to polar pole in 2a. One is root 2, 5 by 4, 5, and another is minus root 2, 5 by 4, and 5. Now we want to calculate from cylindrical to Cartesian coordinate system. For this example, we want to get back this Cartesian point from this cylindrical point, and that is for this representation. We see what will be happened. Root 2 5 by 4, 5 is divided by r, theta, and we know that x equal r cos theta. R cosine theta had r is root 2, and cosine cos theta 3 with this 5 by 4. We know that cos 5 by 4 1 by root 2, that we have 1. Also y equal r sin theta, which is root 2, sin 5 by 4. This result is also 1, and we know that z equal to 5. Therefore, the required point of root 2, 5 by 4, and 5 in cylindrical coordinate system is 1, 1, and 5. So we have successfully, and we come back to this point 1, 1, 5. And we are trying to get back this point by another representation. So we see what will be happen there. X equal r cos theta, r equal minus root 2, and cosine 5 by 4. We know that cosine 5 by 4 is equal to minus 1 by root, which result is 1. And y equal to minus r sin 5 by 4. We also know that the result of sin 5 by 4 is minus 1 by 2. So this result is 1. And z is then z equal to 0. So minus root 2, 5 pi by 4, 5 will also less than 115. So we can easily say that actually in cylindrical coordinate system and the representation of the point there are in two ways. In two methods we can describe or locate a point in cylindrical coordinate system and proof for this result. Dear learners, finally we are going to finish two important work of them. Number one is you have given location of a point. Now you will have to find out the position where it is situated. And another thing is you have given a point on space. Just now you have to locate what is the position of this point. Now we are going to complete the task. For this, I have already given or drawn a picture on the board for saving our time. We have the cylindrical system and has 2 points. I have given location of 2 points. So now I have to find out the point on space. So what will be our procedure? Here, in previous discussion we said that this is polar distance, which will be also described by this line segment where the surface intersects the x-axis, and this focus will R. And with the positive x-axis, this polar distance makes an angle theta. And we have got a point which is r theta. And from here on this plane, we have to move along z direction, upward or downward. So we have given 1 pi by 2 and then minus 1. So we have to start from origin. For 1, we will have to move along x-axis where intersect the surface of cylinder at x-axis. So this is 1. And from here, anticlockwise, we will have to move pi by 2 angle. If we move anticlockwise, then we have to move in this way. In this way, we have got a point at pi by 2. This is r theta. That is theta equal 90 degrees. And from here, he has said that we will have to move along that direction 4 units in downward. So we will have to move from here in downward. That is z is equal to minus 4. I again repeat this procedure. We will have to start from pole or O. Then we have to measure this amount along x-axis. We have got this point. And from this point, we will have to move with an angle pi by 2 anticlockwise. Anticlockwise, if we move on this R, we have got a point r theta, which is 1 and pi by 2. And lastly, for minus 4, we will have to move negative z direction 4 units. Then we have got a point there, which is P 1 pi by 2 and minus 1. Again, if we find out the point Q minus 1. So from the pole we will have to move opposite direction minus 1. That is minus 1. So we have got a point here is for minus 1. From pole we maintain a distance minus 1 with the opposite direction of this 1. So we are here. From here, we will have to move anticlockwise to 70 degrees. If we move anticlockwise from here to 70 degrees, we have already anticlockwise 90 degrees, and this is 180 degrees. If we move anticlockwise 180 degrees, then we are here. And from here, we have reached there, then we completed 270 degrees, by 2. And if we make the angle 3 pi by 2, So we are here at this point r theta, which is -1 and 3/8, -1 and 3/8. And we see that we have to move negative z direction for 4 units. So from here we have to move downward for 4 units. So actually we are at same point P. That is, this is Q -1, 3π/2, and -4. So we see that these 2 points are actually one point in the space. And in previous discussion, we saw here every point cylindrical coordinate system has 2 identities, or a point can be measured in 2 ways, and has the proof for such. Now, the second item is you have given a point. On space or a cylindrical surface. You will have to point out or locate this position like such way. Suppose you have a point is here. It is P or P1. So you will have to locate this point or find out the position of this point with 3 items. For this, you have to draw a perpendicular on this plane. You have to draw a perpendicular on this x-ray, and we have drawn a perpendicular on this x-ray plane from P1, which indicates actually we have made Z. This is Z. And this perpendicular is denoted by Z, which is located at positive direction. Now we have to joining this point with pole. Joining this point with pole, this is our R. In cylindrical coordinate system, if we join and pole and the projected point, then it is R. Now we have to measure the angle with positive x-axis with this polar distance R. Then if we measure the positive axis angle with positive axis, then we have to move from here to anti-clockwise. This is theta. I again repeat this. You have given a point P1, then we will have to locate this point, or we will have to find out the dimension of this point. For this, we will have to draw a perpendicular from P1 to x-y plane, which is Z. Then you will have to join this point from pole. This is polar distance R. Finally, you will have to find an angle with this polar distance from for positive x-axis. Then you have to move from positive x-axis to anti-clockwise up to the polar distance. Then you have to, then we can make the angle theta. So in this procedure, we can find out the location of the point in anywhere in this cylinder, and we so that both cases we have to draw such like cylindrical format for structure, and then we can be able to find out the location of a point. If we have given the location, we can also find out the point where it is situated on the space. Also, if a task is given that a point should be located in this 3 dimension, we can also calculate this with the procedure by projecting, by line joining, and by making line. So, dear student, this was my today's discussion on cylindrical coordinate system, and I think that you have got a rhythm think about this coordinate system, and if you practice properly, I believe that you will be able to calculate all other calculations related to this coordinate system, basically for physics students and for mathematics students in geometry and calculus, and for engineering a student can calculate his magnetic field, electric field, and temperature field, and he or she will be also able to find out the gradient of a scalar field, divergence of a vector field, curl of a vector field, and he can also measure the flux of a flow in fluid dynamics and any other calculations. So thank you everyone for staying with me. We meet again with another coordinate system. Thank you and once again.